Land surface temperature retrieval of Guwahati city and suburbs, Assam, India using Landsat data. Abstract, LST is the surface temperature of the Earth's crust where the heat and radiation from the sun are absorbed, reflected and refracted. LST changes with a change in climatic condition and other human activities where the exact prediction becomes challenging. Drastic changes in the land cover with the decline in vegetation and water bodies due to anthropogenic activities enhances the heat emission from land surface and atmospheric temperatures. Increased land surface temperature, LST, is mainly due to increase in concentrated human activities. Abnormal LST causes drought, depletion of ozone layers, diseases, and also affect crops production. In this study an attempt has been made to estimate LST over Kamrup Metro District, Assam, India, using Landsat 8 of May 2018 and Landsat 8 imagery of January 2019 satellite imagery. The variability of retrieved LSTs has been investigated with respect to Normalized Difference Vegetation Index, NDVI, values for different land use types determined from the Landsat visible and near channels. Identification and characterization of urban heat island, UHI, is typically based on LST that varies spatially, due to the non-homogeneity of land surface cover and other atmospheric factors. The images were converted from DN to TOA radiance using algorithm specified in the Landsat User's Guide. Keywords, NDVI, land surface temperature, LST, land surface emissivity, LSE, NDVI, OLI Landsat 8 imagery, remote sensing, TOA radiance. Introduction. Land surface temperature, LST, is defined as the temperature at a particular location on the Earth's surface. It is synonymous with global temperature, GT, sea surface temperature, SST, and land surface air temperature, LSAT. The remote sensing method of estimating surface temperature has the following advantages: large area coverage, ability to estimate temperature in accessible areas, very efficient and effective method, and above all, is cost-effective. Remote sensing through thermal scanning of entire surface types, plants and soils, simultaneously, express their temperature responses comparable to the atmospheric and radiant inputs. An Earth surface feature emits thermal radiation at different wavelengths depending on their emissivity, E. Emissivity is defined as the ratio of the spectral radiant emittance of a gray body to that emitted by a black body at the same temperature. Accurate land surface emissivity values aid in reliable inferences among different land covers for retrieving LST from thermal infrared, TIR, data. Land surface temperature and emissivity are prime variables to determine the amount of thermal infrared energy radiated from the Earth's surface according to Planck's law. These variables will provide information of many different types of Earth surface processes, surface-atmosphere interactions, and evapotranspiration. The estimation of LST over the Earth's surface is very important for the understanding of the relationship between biotic and abiotic components of the environment. LST has direct impacts on crop productivity. Surface temperature affects groundwater quality, groundwater temperature. The aim of this study is to evaluate the performance of LST retrieval methods using different LSE models and current Landsat missions. To efficiently perform this work, an ArcGIS toolbox, including all the methods and models analyzed here, was implemented and provided as a user facility for the LST retrieval from Landsat data. 2. Study area. Fig. 1. The present study area is Guwahati and surrounding part measuring about 845.77 sq.km, encompasses major part of the Kamrup metropolitan district of Assam, Fig.1. Guwahati is a part of Kamrup Metro District and situated between 25°59'43.604 N and 26°16'22.375 N latitude and between 91°33'13.752 E and 92°3'59.759 East longitude covering topo sheet No 78N/12 and 78N/16 located on the banks of the Brahmaputra River, Fig.1. The city being most important city in entire northeast India, experienced aerial expansion several times during its history. This expansion of the city area had taken place mostly due to the need for coping up with increasing population pressure. Hence in course of time the city changed nature from a small town in 1901 to its present form of capital city with cosmopolitan culture. 3. Materials and methodology. The methodology carried out here using ESRI's ArcGIS 10.5. It was used to perform image clipping, conversion of DN to TOA radiance, estimation of LST, derivation of vegetation indices and for the compilations of maps. Entire methodology is given in flowchart Fig. 2. Land surface temperature is estimated using Landsat imagery of 2 epochs. The images are downloaded from website, glovis.usgs.gov. The images were radiometrically corrected by the data provider. However, before computing surface temperature, the images were converted from digital number, digital count or gray value, to top of atmosphere, TOA, radiance which represents the actual reflectance from the Earth's surface. The DN is a dimensionless unit and does not represent any physical quantity, hence, the need for its conversion. The conversion and computation of surface temperature follows the formulae. I. Top of atmosphere, TOA, radiance. Using the radiance riscaling factor, thermal infrared digital numbers can be converted to TOA spectral radiance. L equals ml * plus AL. Where L equals TOA spectral radiance, Watt/m2 *SR *m. ml equals radiance multiplicative band, no. AL equals radiance add band, no. Cal equals quantized and calibrated standard product pixel values, DN. 2 Top of atmosphere, TOA, brightness temperature. Spectral radiance data can be converted to top of atmosphere brightness temperature using the thermal constant values in metadata file. BT equals K2/LN, K1/L plus 1, 272.15. Where BT equals top of atmosphere brightness temperature, degree C. L equals TOA spectral radiance, Watt/m2 *SR *m. K1 equals K1 constant band, no. K2 equals K2 constant band, no. 3 Normalized Differential Vegetation Index, NDVI. The Normalized Differential Vegetation Index, NDVI, is a standardized vegetation index which calculated using near-infrared, NAD5, and red, band 4, bands. NDVI equals, near, red, / near plus red. Where red equals DN values from the red band. Near equals DN values from near-infrared band. For OLI data, near-infrared band is the band 5 and red band is the band 4. These bands were carefully selected in the map algebra. The values of NDVI map ranges from -1 to 1 which indicates the variations of green and healthy vegetation type in the given area. The higher the NDVI value the denser the vegetation and the lower the NDVI the less dense or absent of vegetation cover. 4. Land surface emissivity, LSE. Land surface emissivity, LSE, is the average emissivity of an element of the surface of the Earth calculated from NDVI values. PV equals, NDVI, NDVI min, / NDVI max plus NDVI min, caret 2. Where PV equals proportion of vegetation. NDVI equals DN values from NDVI image. NDVI min equals minimum DN values from NDVI image. NDVI max equals maximum DN values from NDVI image. E equals 0.004 * PV plus 0.986. Where E equals land surface emissivity. PV equals proportion of vegetation. V, land surface temperature, LST. The land surface temperature, LST, is the radiative temperature which calculated using top of atmosphere brightness temperature, wavelength of emitted radiance, land surface emissivity. LST equals, BT/1, plus W *, BT/14380, *, LN, E, where BT equals top of atmosphere brightness temperature, degree C, W equals wavelength of emitted radiance. E equals land surface emissivity. For results and discussion. Analysis of NDVI and surface temperature. The NDVI map for the month of May shows that the NDVI value ranged between -0.1195 to 0.5822. The resulting map shows moderate NDVI whereas area under water body has significant low value, Fig 3. C:\del\del/desktop\NDVI May 2018.jpg. Fig. 3. The NDVI map for the month of January shows that the NDVI value ranged between -0.121 to 0.433. The resulting map shows high NDVI, Fig 4. C:\del\desktop\NDVI 19 January.jpg. Fig. 4. Figure 5 shows the spatial distribution of surface temperature of Landsat 8 for the month May 2018. The LST ranged from 12 degrees Celsius to 28 degrees Celsius over the study area. It is observed that left part of study area, from left side of the Virchariali nearby, Guwahati Airport, to Nunmati on other side, Beltala on the southern side exhibits high temperature mainly due to high density build-up land. C:\del\users\del/desktop\May18new.jpg. Fig. 5. As the central part of the city have high altitude hilly areas, so temperature falls in some part due to altitude variation. There is also a temperature variation due to river Brahmaputra flows through the Guwahati city. The minimum temperature is found over water bodies, wetlands, waterlogged areas, and high-altitude forest land ranging from 12 to 17 degrees Celsius found on right side of study area in Chandrapur-Digirati region. The impact of vegetation is clearly seen as low temperature values are observed over agricultural land, dense vegetation, forest, water bodies, and wetland categories. LST temperature ranges and areas for the month of May 2018 are shown in Table 1. Similarly, Fig. 6 shows land surface temperature, LST, of Guwahati in January 2020, during which LST ranges from 15 degrees Celsius to 25 degrees Celsius. Here also left side of study area, from the Virchariali up to Nunmati, having high density build-up land having higher temperature ranges, 21 degrees C 25 degrees C. Similarly, right side of study area, Chandrapur-Titalia, having high altitude forest wetlands agricultural lands shows low temperature, 15 degrees Celsius - 18 degrees Celsius. LST temperature ranges and areas for the month of January 2019 are shown in Table 2. V. Conclusion. NDVI, LST of the area was determined using ArcGIS. NDVI maps shows that vegetation is high in the month of May when compared with the month of January. That means, vegetation has been increased, which shows an impact on the surface temperature. Estimated LST values reveal that in the month of May 42.18% of the total area, surface temperature lies in the range of 22 to 28 degrees Celsius, and in the month of January 27.28% of the total area, surface temperature lies in the range 20 to 25 degrees Celsius. In the present study case, as we move away from the built-up areas, LST decreases from high to moderately high or low temperature. As noted in the mangrove wetland, the LST was moderately high to low value. This was due to the regulative ability of wetland to shade water in the wetland from the hot day temperature and from the anthropogenic radiation from urban areas. The very low LST observed in the water body may be due to the ability of water body to absorb heat in the day, and similarly in high density forest, hilly area, agricultural land also LST is low.